Okay, here we go with finding the rate law based upon the information given. So when we want to find the rate law, we've got our rate, and it is equal to the rate constant times the concentration of nitrous oxide raised to some power we're going to call m, times the concentration of H2 raised to some power we're going to call n. So those unknown variables, they describe for us what kind of factor that the concentration of that particular reactant plays into the rate. So as concentration decreases, usually the rate decreases as well, and it decreases varyingly depending upon what the concentration is. So what this does is it takes into account then how much the concentration factor affects that rate right there. So we need to find out what those numbers are, and those are what's called the order. So we can figure out what the order of nitrous oxide is and what the order of hydrogen is based upon our data here. So what we want to try and do is we want to usually try and find data where one thing changes and something else stays the same. So the reason we do that is because we can't have more than one variable. So if we take a look at experiments 1 and 2, with experiment 1 we had 0.2 of the nitrous oxide and 0.3 of the hydrogen gas. With experiment 2, we had 0.1 of the nitrous oxide and 0.3 of the hydrogen gas. So you can see the hydrogen gas stays the same. That's good. That's one variable that's not going to change, or one thing that's not going to change. But the nitrous oxide doubles from 2 to 1. So we can use that then to figure out, all right, so if the concentration of H2 stays the same, but we double the concentration of NO, how does that affect the rate? And so if we look at those two pieces of information, we can see from there to there that the concentration doubled, and from there to there, the reaction rate actually quadruples. So it went up by 4. So the way we look at this then is we say, okay, if the, we look at the factor by which the concentration changed, raised to a power, we'll call it x for now, and that should equal the factor by which the rate changed. What I mean by that is the factor by which the concentration changed was 2. We'll raise that to some power x. We want to make that equal to the factor by which the rate changed, which was 4. So 2 to what power equals 4? That's right, 2. What that means then is that the reaction is second order with respect to nitrous oxide. So it is second order with respect to nitrous oxide. So let's start rewriting our rate law. Rate is equal to the rate constant times the concentration of NO. And now we know that since it is second order, we can put a 2 right there. Now we've got to do the same thing with H2 to figure out what order it is. And to do that, we're going to have to pick an experiment or 2 experiments where H2 changed but nitrous oxide didn't, and we can get that from experiments 2 to 3, or 3 to 2. So we see there that nitrous oxide stayed the same, but H2 increased. And the concentration increased by a factor of 1.5. We're going to raise that to some power x to figure out what effect it had on the rate. And the rate also increased by a factor of 1.5. So that means that x has to equal 1, which means that the reaction is first order with respect to hydrogen gas. And so that means up here in the little corner there would be a 1, or you could just leave it blank. I'll draw that 1 in there just so we know. So that right there is the rate law. When it's asking you for a rate law, it's not really looking for numbers, okay, and it's not looking for words. It's really just an equation that it wants. And on that equation, its rate equals the constant times the concentrations raised to their particular power. And make sure you have those powers put in there. You don't just put the m and n. All right, now let's find the rate constant for this temperature. So the rate constant is a constant, which means it stays the same. So in order to calculate our rate constant, we can really pick any of these experiments on the board. Okay, as long as we use the information from just one experiment, so you can't use the concentration from that one and from that one and from the rate from this guy. You just have to use all 3 pieces of data from the same experiment. But you can pick any experiment you want. I'm going to use experiment 1 and just plug these numbers into the equation, solve for k, and figure out what the rate constant is. And it doesn't matter. You can pick any of these three and you'll get the same K. So rewrite this equation. K is equal to the concentration of, it's equal to the rate divided by the concentration of NO squared times the concentration of H2. So we can just take those numbers from that first reaction, which was 0.900 or 0.090 and molar. Let's write that again. So 0.0900 molar divided by the concentrations at that point, and so it's 0.20, and that's molar seconds. Molar, and that one would be squared, times the concentration of 0.30 molar. And when we do this, we find out that the rate constant, K, is 7.5. Now, what are the units for K? K has different units. It depends on the order of the reaction. It depends on what our reactants are. And so you're going to have to derive them every single time you do this, which is why it's important that you do write your units into your equation. Because in order to derive them, we show what cancels out. So we've got molarity on top and molarity squared on bottom. That means the molarity will cancel out one of those down there. And we have the seconds right there with nothing to cancel them out. And so we're left with 2 molars on the bottom and 1 seconds on the top bottom, so that would be on the bottom, which means that our units for this guy are going to be molarity inverse squared. So that means there's 2 molarities on the bottom times seconds inverse. Another way of writing those exact same units, and either one would be correct, is 1 over molarity squared times seconds. So there you go. That's the rate constant. That rate constant is going to stay the same as long as the temperature stays the same. So we can use it to figure out what the rate is at any given point in time in this reaction, as long as the temperature stays the same. And then the last question is just asking us for the overall reaction order. So the overall is just the order of the 2 respects added together. And so that would be 2 plus 1, which, if I can do this in my head correctly, comes out to be 3. So that means the order for this reaction overall would be 3rd order overall.